Hello, I am Anna Vivani, a PhD student at the University of Insubria in Como, Italy. And with my presentation, I will explain a research on the structural and microstructural characterization of cesium-lead bromide perovskite nanoplatelets, realized by a combination of high-resolution TM and wide-angle X-ray total scattering techniques, which is the content of our recent publication, for which you can find the reference in the slide below. First of all, I'll give you a brief overview over cesium-lead bromide perovskite nanocrystals. Right after, I will describe our material, the synthesis, and the characterization by many techniques. I present our results and finally conclusions. In the last few years, cesium-lead bromide perovskite semiconductor materials have gained wide interest for their optoelectronic applications. Compared to the bulk form at the nanoscale, their physicochemical properties are not also maintained, but even enhanced, finding application especially in lighting devices, such as display, LEDs, and advanced quantum light sources. Cesium-lead bromides nanocrystals show the typical perovskite structure, consisting of a 3D framework of corner-sharing octahedra, where lead ions are coordinated by bromides and cesium cations occupy cuboctahedral cavities. The determination of structural properties of nano-sized materials through XRD conventional methods is a difficult task. Advanced X-ray total scattering techniques, and in particular the approach based on the device scattering equation computation, are emerging as a successful tool for providing accurate insights on the nanostructure of complex randomly oriented samples. A well-established control over colloidal synthesis of cesium-lead bromide nanocrystal is currently achieved, and novel synthesis for highly anisotropic stable nanoplatelets was developed by the Kovalenko group in ETH Zurich, reaching a thickness of 3.5 nanometers. A narrow bright blue photoluminescence with high quantum yields is exhibited, and fine tuning of maximum emission energy is achieved in the whole visible spectrum through fast and efficient anion exchange reactions. Thanks to their monodispersity, upon dropping the suspension, the nanoplatelets self-assemble with a long-range order along the stacking direction, as visible in transmission electron microscopy images. In the small angle region of XRD pattern, the stacking leads to a sequence of peaks with a periodicity of 6.5 nanometers that corresponds to the thickness of nanoplatelets plus the surrounding organic ligands. Different polymorphs are reported for cesium-lead bromide perovskite structure, which differ from each other for the bending of lead-bromide-lead angles. And the orthorhombic symmetry is characterized by octahedra tilted in equatorial and axial directions with respect to the archetypal cubic structure. High-resolution DM images show an interplanar distance of about 5.8 angstrom measured between columns of lead ions running parallel to the facets of nanoplatelets. It's worthwhile noting that this feature is common to both cubic and orthorhombic polymorphs, and this fact indicates that the orthorhombic face retains a pseudocubic facing. However, in the orthorhombic structure, the tilt of octahedra is below the resolution limit of TM. Therefore, the structural polymorph cannot be directly assessed by the high-resolution TM. And the wide-angle X-ray total scattering methods, WAXTS-DSE, are able to model both Bragg peaks and the diffuse scattering intensity, and applied to high-resolution data, made possible the quantitative determination of cesium-lead bromide nanoplatelets' structural properties, as well as sizes, morphology, and effectiveness. WAXTS measurements have been performed using a synchrotron source on colloidal suspensions at the Material Science beamline of the Swiss light source at Paul Scherrer Institute, using a device Scherrer transmission geometry setup spinning capillaries filled with suspension, and meet-and-chew detector. After collection, a data reduction procedure has been applied to raw data, consisting of correction of absorption effects and the subtraction of the extra sample scattering contribution coming from capillaries and hair. Within the DSE-based approach, atomistic models of nanocrystals are built, from which the interatomic distances are computed and used to calculate the biscattering equation. In particular, we developed the nanoplatelets model by stacking monolayers of tilted octahedra, and we created a bivariate population of nanoplatelets grown along two independent directions, one parallel to the nanoplatelet's thickness and the second one perpendicular to basal planes. Finally, the model was optimized by refining structural and microstructural parameters against experimental data. And the model refinement was carried out using the Debussy suite of programs developed at Tosca Lab. The orthorhombic structure in PNMA space group has been confirmed by total scattering data refinements. And with respect to the cubic model, the orthorhombic polymorph provided better agreement with experimental data. In this setting, nanoplatelets expose 101 and 010 orthorhombic facets corresponding to 100 pseudocubic facets. Bromides are not equivalent in the orthorhombic structure, hence the issue of addressing the relative orientation of crystallographic axes with respect to the nanoplatelet's morphological edges becomes of high relevance. And considering that the A and C unit cell axes, as well as the two longest morphological directions, are closely similar in length, we found out two meaningfully different orientations to investigate, labeled T100 and T010, referring to the cubic indexes. The first configuration in the left side of the slide implies that the axial bromides in yellow are nearly aligned to the nanoplatelet's thickness, and that the equatorial bromides in red points towards the basal planes. The second configuration shown in the right side of the slide is characterized by the opposite arrangement of halides. For such thin plate-like nanocrystals, the diffraction signal and in particular the Bragg peaks component is strongly influenced by complex effects related to the combination of highly anisotropic morphology with the huge amount of diffuse scattering, which is typical of crystal domains having limited extension. These effects are here exemplified by comparing X-ray wide-angle simulation of cuboidal nanocrystals and nanoplatelets, having the same unit cell parameters and equivalent volumes. Indeed, among these different cases, shifts in position and peak shape variation of Bragg peaks are observed, depending on the contribution of inequivalent reflections lying underneath broad peaks. It is clear here that the precise determination of lattice parameters can be negatively affected. And therefore, a grid search algorithm was implemented to optimize the cell parameters for both of the selected configurations, upon fixing all the other model parameters, avoiding misinterpretations related to morphological effects. Ranges for the three crystallographic axes were explored. For each combination of those, a DSE simulation was performed and compared to experimental data. The resulting hypersurfaces are projected in the slide as 3D maps of the goodness of fit statistical indicator versus B and C lattice parameters at constant A values. The minimum of GOF at 1.73 points to the configuration model that exposes equatorial bromides in the basal plane and axial ones aligned to the nanoplatelet's thickness as the best model. Notably, this model reveals a remarkable cell volume expansion of 1.74% if compared to the bulk powder material. And the lattice expansion is anisotropic, exhibiting the largest expansion along the B-axis, that is the direction along which run the axial bromides. And this experimental finding agrees with recently reported DFT calculation, suggesting that lead-alide perovskites exhibit markedly different elastic constants, in particular between the axial and equatorial lead-alide direction. Despite the fact that the X-ray diffraction technique is not devoted to surface analysis, total scattering methods can become sensitive to superficial features when samples have a high surface-to-volume ratio, which is especially true for plate-like nanocrystals. And in order to investigate the termination of cesium-lead bromide nanoplatelets surfaces, the best atomistic and morphological model was used, considering for it three alternative surface descriptions. First, cesium bromide terminated surfaces. And this model implies that half of cesium sites and half of bromide sites at the nanoplatelet surface are vacant, with a fully stoichiometric composition. And this model provided the best agreement with experimental data. A bromide-rich surface model with cesium vacancies only and a lead-bromide terminated model were also investigated, but both provided worse agreement with experimental data. To conclude, in this work I presented the synthesis and the full characterization of stable monodisperse 3.5 nanometers equal to 6 octahedra monolayers thick cesium-lead bromide nanoplatelets, and an accurate structural and microstructural characterization was provided. As future perspective, the results here presented encourage to extend this kind of analysis to other nano-sized materials belonging to the class of lead-alide perovskites. And I would like to thank you, all the people involved in this study, the Giovani Cristallografi Italiani Association, and you for your attention.